Hello and welcome. We are starting the unit of rational functions, and this is the first lesson, the graphs of reciprocal functions. I decided to start with the reciprocals of a linear and quadratic function because I think that they will allow us for a smoother transition to the fascinating world of rational functions, which, on the other hand, I think are quite misunderstood because they're perceived as quite complex to draw, but as a matter of fact, they're easy to understand and a lot of fun to draw too. This lesson has been prepared for students who are taking the grade 12 Advanced Functions course, MHF4U, and this is the math you take in grade 12, and it's recommended that you take this course before you take calculus. So let's get started. When we add, subtract, or multiply polynomial functions, the result will be another polynomial function, which will exhibit the same properties as the functions it was made of, the functions that you added, subtracted, or multiplied together. On the other hand, when we divide two polynomial functions, the result will be a rational function. And because rational functions have restrictions, they will exhibit special properties and their graphs would look uniquely different. So let's get started with the reciprocals of linear functions. And as a first example, I took the reciprocal of a linear function, which I'm pretty sure you have graphed in grade 11, but we're just going to refresh our memory. First, we're going to draw the graph of Gx equals x. So this is a straight line with a y-intercept and x-intercept at 0, 0. And it makes an angle of 45 degrees with both x and the y-axis. So let's name the graph. This is g of x. And now we are going to draw the graph of its reciprocal. For this, we're going to refer to some key points. And I'm pointing at the first one, 0. When x equals 0, y equals 0. Remember, we are reciprocating the y values. Okay? So the y values of the line. So y equals 0. Division by 0 makes no sense, though this will translate to no point for the reciprocal. Next point is x equals 1, y equals 1. So the reciprocal of y equals 1 is 1 over 1, or simply positive 1. This point here, y equals 2. The reciprocal of 2 is 1 over 2. Next point, y equals 3. The reciprocal of 3 is 1/3. Y equals 4. Reciprocal of 4 is 1/4. And you can imagine how as we allow x to approach infinity, the values of y will approach 1 divided by infinity. Now let's think about the value of 1 over infinity. Imagine you have $1, you're sharing it with an infinity number of people. Practically everyone would get nothing or $0. But mathematically speaking, we're going to say that everyone gets to have slightly more than $0. So we are going to say in this case that the y values will approach 0 plus, and the symbol plus that I added here on top just means that it's slightly more than 0. Okay? It's a very negligible plus, amount of plus, but it's still there, so we have to show it. So this would be the shape of the graph for the y values for this portion of the domain, or for this portion of the graph. Now let's take a look at what happens between x values 0 to 1. The y value at this point here is 1/2. The reciprocal of 1/2 is 2. I'm getting closer to x equals 0, so I'm getting x equals 3. The reciprocal of x equals 1/3, sorry. So the reciprocal of 1/3 is 3. The reciprocal of 1/4 must be 4. And that will help us shape the graph for the other portion of the domain. So from 0 to 1. In the same way, we'll continue with the x values in the negatives. So from negative infinity to 0. Again, we'll refer at this very important point. We always refer to the points where y equals 1. Okay, it's a very important point to show on the graph. So when x equals a -1, y is -1, and the reciprocal of -1 is also -1. So this will be a point on the reciprocal. At x equals -2, we have here y equals -2. Reciprocal of -2 is -1/2. Reciprocal of -3 is -1/3. Of -4, -4, and so on. So from -1 to 0, I'm going to take -1/2. We'll have a reciprocal. So this point here has the y value -1/2. Reciprocal of it will be -2. So let's plot this point. And then -3, -4. So it will follow the same pattern. Okay, so this is the shape of 1/x. Now, as you can imagine, as x approaches negative infinity, the y values will approach 1 divided by negative infinity, or in other words, we're going to say 0, but slightly less than 0 because the y values will be below the x-axis, which means less than 0. Another very important feature of this graph is the asymptotes. Remember that x was never allowed to be 0, and that will allow the graph to have an asymptote in the vertical direction, and we call it vertical asymptote at x equals 0. And similarly, it has a horizontal asymptote at y equals 0. So with this, we have completed drawing the graph of 1/x. Now let's talk about the intercepts. I'm going to start with g of x. G of x has an x-intercept at 0 and a y-intercept also at 0. As x approaches infinity for g of x, oopsie, x approaches infinity, y approaches infinity. And when x approaches negative infinity, y approaches negative infinity. Now, the function, as you can see in here, if you read it from left to right, the pencil will go up. So that means the function is increasing for any real number. Or you can simply write from negative to positive infinity, since it is asking for interval. And, oops, sorry, I wrote this in the decreasing interval, so let me just move it. So it's always increasing. It's never decreasing, so we're going to write non-applicable here. And the point where y equals 1 is when x equals 1. And when x equals -1, y will be -1. Now, for the reciprocal, we're going to say that there are no x-intercepts and there are no y-intercepts. Now, very often when I ask my students to state the x and the y-intercepts in the rational, because there is none of them. Now sometimes that's happened that they write this. There is none, so there is 0. If you write x-intercept 0, that means that there is an x-intercept at x equals 0. So try to avoid describing no x-intercepts by using numbers. Just use words. Now, as x approaches infinity, we said that the y values will approach 0 plus. As x approaches negative infinity, 0 minus. And as x approaches 0 from the right side of it, so this is x equals 0, that's 0 plus. I'm going to say that the y values are going all the way up to infinity. And as x approaches 0 from the left side of it, the y values will approach negative infinity. Now let's check and see if we have intervals of decrease. I'm going to start with the left end, far left end of the graph, and I will follow the graph, and I notice that my pencil is going down as I read the graph left to right. So that's an interval of decrease, I would say. So it's decreasing from negative infinity to 0. Now I'm going to read the next piece. So I'm going to start from the left end of the graph for the next piece, and then read left to right, and I see that the graph is also decreasing, so from 0 to infinity. So there are 2 intervals of decrease, and notice that there are no intervals of increase because they're all occupied by decreasing intervals there. And the function will have a value of 1 at x equals 1. We're talking about the reciprocal again. And the function will have a value of negative 1 at x equals negative 1. Now, just like we drew the graph of 1 over x, now we're going to draw the graph of negative x. So for this, we're first starting with m of x equals negative x. I'm going to draw the graph of this very familiar line. It has a negative slope, and y-intercept and x-intercept are both at 0, 0. Let's start reciprocating it. So we're drawing the graph of 1 over mx. So we're looking at the y values. So I'm going to start from the left end of the graph. So here y is negative 3. That will make, yes, at negative 3, the y value will be negative, at x equals negative 3, y will be 3. So 1/3 for the reciprocal. Y is 2, 1/2 for the reciprocal. Y is 1, reciprocal is 1. Y is half, reciprocal will be 2. Y is a quarter, the reciprocal will be a 4. Okay, for the same x value. So there goes the first portion of the graph. Now, in the same way, we're going to continue with the next part of the domain, or the next portion of the graph. And I'm going to say that when at this point we have the y value equal to 1, the reciprocal of 1 is 1. That's one of the key points we look at. Y is 2, the reciprocal will be 1/2. Y is 3, the reciprocal is 1/3. Y is 4, 1/4. Now, similar to this, y is 2, the reciprocal would be, y is negative half, the reciprocal would be -2. Now at this point here, y is a quarter, the reciprocal will be -4. And then we'll connect the points. And obviously here, y is -1/3, -3, so we try to connect the point as smoothly as possible. And there goes the graph again. And here are the asymptotes. So we have a horizontal and a vertical asymptote. So the horizontal asymptote is at y = 0, vertical asymptote at x = 0. So we can continue now with the description of the functions. M of x equals -x will have an x-intercept at 0 and a y-intercept at 0. And that will translate to no x-intercepts in here and no y-intercepts. And because there are no x-intercepts and these are restrictions, we're going to have a vertical asymptote at x = 0 and a horizontal asymptote at y = 0. Now for the function mx, m of x, as x approaches positive infinity, here is x approaching positive infinity, the y values are approaching negative infinity. And as x approaches negative infinity, the y values are going higher to infinity. For the reciprocal, we say that as x approaches infinity, the y values approach 0 from below, so 0 minus. As x approaches negative infinity, the y values will approach 0 from above. As x approaches 0 from the right end of it, so 0 plus, the y values are going all the way down to negative infinity. And as x values are approaching 0 minus, the y values are approaching positive infinity. 0 minus, positive infinity, that's where the graph is. So there we go. Now if you look at function m of x, then you can tell that as you go left to right, the function is decreasing, so there is an interval of decrease for any real number x, or we can simply say for x from negative to positive infinity. Now, if a function is decreasing for any real number, then the reciprocal of it will increase, so we'll do the opposite, because the reciprocal of a decreasing quantity is an increasing quantity. I hope this makes sense. Think about the reciprocal of 1/2 and the reciprocal of 2, right? So we're going to say that the function is decreasing for the same from negative infinity to infinity, and its reciprocal must be increasing. From negative infinity to 0 and from 0 to infinity. So no decreasing intervals for the reciprocal and no increasing for the given function. So where are the points where y = 1 and -1? It seems that they are still very agreeable. So when x equals -1, y would be +1 for both of them. So x equals -1, y would equal 1. And for x equals 1, y would equal -1. So these are the two simplest reciprocal functions. We'll continue now with two other reciprocals of linears. So this time I've chosen the equations g of x equals 2x minus 3, and let's make this perfect, and the function f of x equals 1 over gx. I'm going to start by graphing g of x. G of x will have the y-intercept at negative 3 and the slope of 2. So it will be made of these points. I'm going to make this a little thicker, maybe it's going to look better. Okay, not bad. So this would be 2x minus 3. Now let's talk about the intercepts. Now notice how whenever we discuss the reciprocals, as we go from one example to the other, we start graphing them more easily and a little bit differently as well. So we're going to start with the intercepts of Gx. So the x-intercept for g of x is, look at this one right here, you can tell that is at 1.5 or 3 over 2. And the y-intercept is at negative 3. Now we're going to graph the reciprocal of it. So we are starting with this central point in here. So when x equals 1.5, the y value will be 0. So the reciprocal of the y value, which is 0, doesn't exist. So guess what? Here, the graph will have a vertical asymptote. I'm trying to draw a broken line here, but I'm simply going to change the color. I have to change this one. So it's sort of halfway, that's good. And then I'm going to look at the important points. Remember the important points we said when y equals 1. So when y equals 1 here at x equals 2, right? Then the reciprocal will also be 1. And then I'm going to look at the next point here, y equals 3. The reciprocal will be 1/3. As we get closer to the vertical asymptote, so here we are at 1.5, so, or 3 over 2. So think of a number to the right of 1.5, say 1.6. So the reciprocal of 1.6 will be a point higher than that. So, or you can look at this point in here where y equals 0.5. The reciprocal will be 2. So the graph is increasing faster here around the vertical asymptote. And that is thanks to the horizontal compression here. So as x approaches to infinity, y will approach 0 plus. The same thing will happen on the other side. So here is y equals negative 1, or reciprocal would be negative 1 still. Here we have y equals negative 3. The reciprocal would be negative 1/3. And then we will continue or follow the same pattern. So negative 4, negative 1/4 for the reciprocal. So there goes the graph of this portion of the linear function. So for this portion of the linear function, we get this reciprocal. And now we're going to take a look at what happens as we get closer to the vertical asymptote. So here we are, y equals negative half, reciprocated will be negative 2. and then -4. So this will be the graph. Now, as you see, again, we have a horizontal asymptote at y equals 0. Y will never equal 0 because we have a numerator here that is different than 0. And you can divide it by anything. It will never give exactly 0. So when you look at or when we look for intercepts for the function 1 over gx of the reciprocal, we're going to say that there are no x-intercepts but we do notice also an asymptote, a vertical asymptote at x equals 0. 1 over 1.5. And the horizontal asymptote will be at y equals 0. And we also this time see a y-intercept. And the y-intercept, let's take a look at it. So the y-intercept happened right here when y was -3. The reciprocal was -3rd. Now, the y-intercept will always be these constant numbers at the end. So the ratio of the constants in a rational function. So we're going to say that the y-intercept is at -3rd. Now let's take a look at the end behavior. So for the linear function, as x approaches positive infinity, y approaches positive infinity right here. For negative infinity, the y values will approach negative infinity. For the reciprocal, on the other hand, as x approaches positive infinity, y will approach 0 from above. As x approaches negative infinity, 0 from below. As x approaches the vertical asymptote at 3/2 from the right, the y values go all the way up to infinity. And as x approaches 3/2 from the left side of it, the y values will go all the way to negative infinity. So intervals where the graph is decreasing, we're going to say for g of x, we have none. But it is increasing for any real number. Or you can say from negative to positive infinity. On the other hand, for the rational function, we're going to say that it's always decreasing for this portion, always decreasing for the other piece, so always decreasing. So we're going to say that intervals of decrease are from negative infinity to 0, joined by 0 to infinity. And there are no intervals of increase. So the value of y would be 1 at the same points, which are at x equals 2. So y equals 1 at x equals 2. And the same thing for the reciprocal. Y would equal 1 at x equals 2. And y will equal -1 at x equals, right here, at x equals 1. And the same thing for the reciprocal. So -1 we said. Alrighty then. So we're coming to the end of reciprocals of linears, and I really wanted to go over one more equation here. So we're talking about the reciprocal of 2 minus x. And I need to fix this as a typo. Okay, so for the function y equals 2 minus x, and I'm gonna make this one here my linear function, and this one here will be the reciprocal of the linear. Okay, so let's graph 2 minus x first. It will be a straight line with y-intercept at 2, and slope is -1, so it will go down at 45 degrees and go with the axis. Okay. Oh no, it's not that good. So let me make this a bit straighter. I think if I move the pencil faster, confidence matters, huh? And I'm gonna fix this one. It's a little bit of cheating here, but no. Math will be mad at me for pretending that I drew a straight line there. I wish I had a ruler here, because actually it's easier to draw a straight line on a piece of paper. I'm recording all these videos on an iPad, and iPads are quite slippery. They have a slippery screen. Here we go. So we're going to draw the graph quickly. Oops, you are not supposed to see these. Okay, what did just happen here? There we go. And here's our m of x. And I'm going to quickly point at the important points that we actually talked about right now. So it will have an x-intercept at +2. It will have a y-intercept also at +2. Now the x-intercept is where the y value equals 0, so that will translate to a vertical asymptote for 2 minus x. So vertical asymptote is x equals 2. And the values of y will never equal 0 because we have a number divided by anything. So there will be a horizontal asymptote at y equals 0. And now we're going to draw the graph of 1 over x. So here we go again. The y value here is 1. The reciprocal of 1 will be 1. The value of y is 2. Reciprocal of 2 is 1/2. Reciprocal of 3 is 1/3. Of 4, 1/4. Now at this point, special point in here, y is 1/2, so reciprocal of it will be 2. And then reciprocal of y equals 1/4 will be 4, and so on. But here goes the graph. On the other hand, we have here y equals -1. Reciprocal of -1 is -1. The reciprocal of -2 is -1/2. And so on. Reciprocal of bigger numbers will go closer and closer to 0. Bigger negatives, right? And then we have the y value at this point, -1/2. The reciprocal will be -2. So we'll continue the pattern this way. And voila, there goes the reciprocal of 2 minus x. So any x-intercepts, we're going to say None that we can see. And that's because the graphs of rational functions will never cross their horizontal asymptotes. And for the y-intercept, we're going to have y equals 1/2. As I mentioned before, the y-intercept is made of the ratio of these constants. So imagine x disappearing from the scene in here. We also see asymptotes here, one vertical asymptote at x equals 0, x equals 2. Who said 0? Nobody. And a horizontal asymptote at y equals 0. All right, now let's talk about the end behaviors. We can do that a bit faster now. As x approaches infinity, the y values will approach negative infinity. X approaches negative infinity, the y values are going up to infinity. On the other hand, for the reciprocal, we're going to say x approaches infinity, y approaches 0 from below. And it kind of makes sense because you are dividing 1 by negative infinity somehow, right? So by these values. Now, x approaches negative infinity, y is approaching 0 from above. X is approaching 2 from the right end of it. The y values are going all the way down to negative infinity. And similar to this again, as x approaches 2 from the right end or right side, the y values are going all the way up to infinity. Now let's talk about intervals of increase and decrease. So the linear function is a decreasing function, so it will decrease for any real number, or we can say from negative infinity to infinity. So if the linear function is decreasing, guess what? The reciprocal will be increasing. So increasing intervals from negative infinity 0 joined by 0 to infinity. Now there are no intervals of decrease for this function. You can tell this is increasing, right? So the line goes up left to right. And there are no increasing intervals for the linear. Now the points where y is 1 and we're going to say y is 1 at x equals, so here is y 1 at x equals 1. And y is negative 1, let's take a look right here, at x equals positive 3. So you can see why y equals 1 is a very important point, because the reciprocal of 1 is 1. So that's a point we want to show on the graph. So y is 1 at x equals 1 and negative 1 at x equals 3. So this is the end of reciprocals of linear functions. And I am going to leave it here and continue with the next video, on the next video with reciprocals of a quadratic. Thanks for watching, and I hope this helped you understand reciprocals of linear just a little bit better than, from long ago.